Hi, welcome to Teardown Tuesday. It's not every day that Tektronix release a new oscilloscope, especially these days, but they have. It's a new MDO 3000 mixed domain oscilloscope, a sort of a lower end follow-up to their MDO 4000, which we've reviewed and tear down before, and I'll put the links down below if you haven't seen that one. So I expect this one to be a similar high quality design and construction inside. It's got the built-in RF spectrum analyzer, which is going to be fantastic to take a look at, and this is the 1 gigahertz version, so it will actually contain different hardware to the lower end 100 to 500 megahertz version, at least on the front end anyway. But oh yeah, so of course we could power it up and review it, but hey, you know what we say here on the EEV blog, don't turn it on, take it apart. And here it is. It is small and lightweight and pretty compact. Well, at least, you know, small and lightweight for the size. I mean, the screen is absolutely enormous on this thing. And, well, I see a couple of screws on the back here. So let's whip it open. It looks like, you know, traditional Tektronix type design here. Just a few screws on the back. The whole back panel will lift off. I can see the boards. The big fan in there. I can see the boards through, or the rear board through here. So it looks like it just whips straight off, and there's a metal shield on top, so there'll be more items in there. Looks like, yeah, this back panel will just lift off. We don't have to undo any nuts on the BNCs there. Maybe on the inside, well, almost certainly on the inside before we can get that metal can off. And of course, this is going to be shielded really well. The spectrum analyzer built in, just like the 4001, will have its own metal die-cast metal can inside there, so there will be some RF porn inside there, no doubts. It's a 3 gigahertz bandwidth. As I said, this is the 1 gigahertz model, and it is physically different to the 100 to 500 megahertz model. If you want to upgrade, if you buy the 100 megahertz model and you want to upgrade to 500 megahertz, you can with just a software license. But if you want to go to the 1 gigahertz like this model is, you have to physically send it back, and they swap the board. I'm fairly confident it'll only be the front end that actually changes, the amplifier on the front end. I don't think any of the processing or anything like that actually changes inside. So really, if we are able to see the analog front end, that'll be the only difference between this and the lower end model. The RF spectrum analyzer, the 3 gigahertz bandwidth one, is the same on all models. Now, of course, Tektronix are famous for their hybrids. They're a huge company, of course, one of the big three scope manufacturers, and they of course roll their own hybrids for all sorts of stuff, their own custom ASIC chips and things like that. So they're notorious for, you know, if they fail, like in the old Tektronix scopes, getting replacements. Very difficult indeed, although of course these modern ones, they're so complex that, you know, you probably wouldn't repair these suckers. Like, you know, in 20 years time, you're probably not going to be able to repair one of these things if it goes haywire. Let's lift it off, because this is my own unit. They did donate it to the EEV blog lab here, so it is now the highest bandwidth scope in my lab at 1 gigahertz. So we're going to have lots of fun playing with this thing over time. And so yeah, I really don't want to damage this. Even if it was theirs, I wouldn't want to damage it anyway. It did get stuck in customs. Sorry for the late notice on this thing, but it did get stuck here, and I had to pay a customs fee to get it cleared and get it into the country. But I was supposed to have this before the launch deadline. It launched on the 25th of February, and I'm sure you can actually buy it right about now. Prices start from, I think, don't quote me, about $3,300 for the base model unit. Looks like there is another second shield under there, because I still don't see the nuts for these BNC connectors. And I am taking high-res photos of this as I go along, so if you want to see those, jump on over to eevblog.com, where they will be linked in. The link will be down below for that. Yes, I've got my new Sony Nex 5T camera with my macro lens. Very nice. Ta-da! And, look at that. We're in like Flynn, and the main board exposed. fantastic. And the power supply up the back, look at that, all very neat. But you'll notice the first thing, of course, is that there's no shielding from the switch mode power supply to the main logic down here. Go figure. Well, not a huge deal in the logic, because this is all the digital logic stuff, you know, around here that's near this switch mode, all the RF, all the stuff that matters, the RF on the front end, of course, RF, the RF spectrum analyzer will have its own metal cam, but all the analog front end for the 4 channels will be all in its own individually shielded thing. But still, in a scope of this quality, I would have expected shielding around the can like that, because that's par for the course in other scopes that are cheaper. So yeah, not that impressed. Now, I do really like this rear connector board like this. PCI card edge connector, which then flips over onto the main board. I really like that. So we didn't have to undo any of the connectors on the back to get it open. This is a really very well designed case. So you can see the thought that's gone into this. Small touches like the fan over here, they've gone, oh, well, you know, ordinarily you would power that from the power supply board over here, but oh, we don't want to run a cable all the way over there. Oh, look at this. Let's make it nice and neat and just the right length and mount it on that rear panel connector board there. You know, absolutely brilliant. The mains wiring, very neat, very tidy down in there. Look, the cable runs have been kept to an absolute minimum. They're cable tied here. They've just got exactly the right length cable to go in there. Beautiful. Now, even though the power supply is unshielded, but I'm sure Tech have done their homework on that, so I'm just nitpicking with the shielding. It's just not best practice, that's all. But they're obviously getting away with it, and, well, okay, I trust Tech to know what they're doing. But the actual power supply looks like very high quality. They've got an Emerson transformer down here, you know, top quality brand. It's all, you know, TUV compliance on it and all sorts of stuff. Looks really, really well designed. Of course, Tektronix wouldn't have done this. They would have shopped this out. But yeah, you know, look at that beautiful Celastic holding everything in place. All your protections are there. Or you've got your boots, even over the earth connector there. We've got a rubber boot over that. Beautiful. We've got some input protection down in there. It's, you know, they're doing everything right on this power supply. High quality, but hey, that's what you'd expect when you pay high price for a Tektronix. And for those who love to know the capacitors, as we all do, and you should, because they should be high quality in a Tektronix, yes, it is a Rubicon brand, no problems whatsoever. And that one, by the way, was 105 degrees C rated, and this one down in here, even though you can't see it, trust me, is a Nippon Chemicon. So once again, top quality and 105 degrees C rated, no problems. Someone really has gone to town with the Celastic gun. Look at all this. It's all gunked down. Just, well, you know, it's beautiful, of course. It looks like we might have some small PCB fuses down there, perhaps. They've got silicon in the end-on through-hole mounting like that. Fantastic. And the pod is sealed. Nice. And the fan, once again, also good quality brand name, Sanyo Denki. No problems at all. So our main processor board is significantly less complex than the MDO 4000, its big brother product, and that's what you'd expect. Why? Well, it's obvious they're trying to meet a much lower price point with this thing, so they're going to sacrifice some horsepower and capability compared to the MDO 4000. And if you compare it, which I'll link in the photos and the video down below for the 4000, well, this has bugger all compared to the 4000. We've only got 3 main heat-sunk devices here to share across all 4 channels. Now, there could be more stuff on the other side, but certainly not big heat-sunk devices like this, whereas the MDO 4000 had, I think, a separate ADC per channel, heat-sunk and all that sort of stuff. But look, 3 main devices. The sample memory here, almost certainly the sample memory. Why? Well, there's 4 of them there, and they're coupled in with presumably match length traces to get the timing right. We'll take a close-in look at that. So there's 1 device per 2 channels like that. So of course your sample rate will halve if you turn on both channels, presumably. And then they've got the 3rd main heat-sunk device over here. That could be a you know, the main acquisition ASIC, or you know, something like that, triggering all sorts of other jazz. But that's tied between all 4 channels. So Really, they have cut costs here. Presumably not the same ASICs as they use in the MDO 4000. I presume that they've spun new ones for this MDO 3000. And here's one of the main ASICs as well, a totally custom job, presumably. Tech part number, you probably can't get any info on that to save your life, no doubt. And they've got some more memory coupled into that here closely. And if you follow the traces out like that, you'll notice that it is coupled into these channels over here. So there we go, you can follow that bus all the way around over into this main ASIC, and presumably on some of the other layers there will be another parallel bus going from here over to that one as well. So this is obviously some sort of main acquisition and processing ASIC, probably does all the DPO intensity grading and things like that, perhaps part of the display ASIC, perhaps. I still don't know where the display is plugged into this thing. So that's the thing with these, when you're doing teardowns like this, you can tell a lot of the functionality due to the proximity of stuff. Like if the display connector was here and then coupled in, well, you know that this is doing the main display processing as well. So anyway, this thing does have a couple of 100,000 waveform updates per second, so they're obviously doing that in hardware instead of the main processor down here, which we'll take a look at, that handles all the GUI and the controls and the communications and all that sort of stuff. And if we have a closer look at those memories, I've checked the data sheets for these, SSI brand of course. These are 8 meg by 32, or a total of 256 meg synchronous DRAM. So there you go, that's coupled. There's two of those, maybe another couple on the back side of the board, we don't know until we flip it over, coupled into this main ASIC. So presumably that would all be for the DPO intensity grading and display processing and stuff like that. That'd be my guess anyway. Until I flip the board and find exactly where the processor, the display is connected into, we won't know. But that's a good first guess, I think. And back over here to the ASIC, which shares two channels, we've got ourselves some Micron memory here. That's the Micron symbol, and you have to decode this part number here, but thankfully Micron on their website have a part number decoder for these small BGAs. They can't print the full number. For those playing along at home, it is actually an MT42H64M16HR, and that is a 1 gigabit or 64 megbit by 16 memory. So where is the rest of it used for? Well, clearly used for the logic analyzer would be my guess. I see dedicated logic analyzer circuitry, but I don't see logic analyzer memory unless we flip the board out. And there's our main clock down in there. It looks like 100 megahertz. Don't know the exact brand. It looks like it's got decoupling on like a little surface mount hybrid module there. That's quite interesting. Hooked into a Analog Devices ADF 4360, and that's a no surprise, a synthesizer and voltage controlled oscillator. So that gives that chip's capable of a 350 megahertz to 1.8 gigahertz output. So clearly that's not providing directly the main sample clock for the ADC. This thing samples at 5 gig samples per second. So there has to be some additional multiplication happening somewhere else. And no surprises for seeing tied into that is a Macrel HEP11U. I had a look at the data sheet for that one, found it. No surprises, it's a PECL buffer. So that's actually providing the drive. Here we go, here's the input coming from the output of the VCO there, coming through here into the buffer, and then so check this out, there's the output there coming across. They're clearly tapping off that signal there and through to the bottom layer, so an internal layer through those vias, and then they've got this massive LC filter network, huge number of stages here, and then popping out the other end there to drive something else. Fascinating. So you've got to wonder if that's some sort of LC delay line or something like that. Now this is rather interesting. Check out this lattice device here. It's a LFE3 series FPGA, and it's not a particularly big beast, and it's not heat sunk, so it's not doing any real serious work, but it's only a 33,000 lookup table FPGA with 1 megbit of memory built in. They've got some ROMs, some flash memory coupled into that, so you've got to wondering, You got to wonder what this thing is doing. Is it running some sort of internal, well, it must be running some sort of internal processor if it's got some flash memory hooked up to it like that. So a soft core processor. But take a look at all of these test pads out here. This is not for an unpopulated connector. I believe that's a, some sort of production test pad or something like that. So maybe, could this be a real expensive and dedicated way to do production testing perhaps? I don't know. Maybe it's doing something else. You can clearly see the traces coupled up here. Look, they're heading all the way up there, coupled into one of the input ASICs over here, as I'll call them, and presumably there would be a similar, no, there could be a similar bus heading on over to the other one. You would think so anyway. So, yeah, what is that puppy doing? On second thought, it's actually very likely to be the serial decoding feature of this thing, because this is like a, advertises 6-in-1 instruments, and that's one of the main instruments is the serial decoding and stuff like that. So maybe they're doing that in hardware in this dedicated FPGA. And it just looks like we have some power supply stuff down there, presumably for that Lattice local regulation core voltages for that Lattice FPGA. And we have ourselves another oscillator. It's one of the Espresso series. Can't quite make out the part number of that, but yeah, presumably just another clock multiplier. And we've got a couple of JTAG headers here, conveniently fully populated with the proper header connector. So go and plug straight in and hack and debug and play around to your heart's content, I guess. And I have absolutely no idea what's going on here. Look at this. It's almost as if it's some sort of big touch sensor. Some capacitive touch sensor. They've got some, digital tracers running underneath there, so that's not good practice to begin with. But, why? Why is that? Look, my finger is, that's sort of like the size of my finger. I wonder what it does. Be interesting to power this thing up and just touch your finger on there, maybe. Because look, there's a couple of vias on there, so it's not, so they're electrically connected in two separate halves. It's not some weird-ass spark gap, input protection thing, because there's no solder mask removed off it or anything like that with the sharp corners. It's a capacitive touchpad. That's all I can figure. And check it out, I found a little bodge in there. Look at that. Curiously, on just one channel of this multi-channel logic analyzer input here. Here's the logic analyzer actual connectors on the other side of the board down in there, presumably surface mount on the other side. And no surprises for guessing these are your input comparators. Yes, very fast ADCMP 562s, 1 nanosecond comparators, 500 picoseconds rise time, differential Peckel outputs. It's all happening there. And just above those is a voltage regulator, but not just any voltage regulator, a fast pulse response voltage regulator specifically for driving these input comparators, no doubt. Because that's the real disadvantage with having extremely fast, devices of any digital nature like this. They take huge gulps of current when they're switching. So really, you need a fast transient response voltage regulator up there, local, just to power those devices. And that's a LDO, 77725. Nothing much happening around here. This ICL 3221 looks important, but it's just a max sort of 232 equivalent part for RS-232 interfacing. That brings us over to our main processor, or main applications processor as you'd really call it, because this is no surprises for finding a Freescale IMX6 series. This is a ARM Cortex A9 processor, 1 GHz. This series of chips, you can actually get quad-core versions, but this is only what's called the solo chip, hence the S in the this 6S there in the part number. So this only has one core in it. But this thing is quite a beast, operating at 1 GHz, capable of 1080p encoding and decoding. Fantastic stuff. So as you can see, we've only coupled in one DDR to memory here. You can see there's an unpopulated footprint on the bottom. There could be another one on the bottom side there, of course. And of course, you notice the serpentine traces. That's to match all the length of the differential pairs going to the DDR memory there. Now, whether or not this thing is driving this display directly, or whether the display is actually handled by this main Tektronix ASIC over here, because if you're getting a couple of 100,000 waveform updates per second, it's going to be hard to do that through even a real beefy applications processor like this. But hey, they could be doing it. So yeah, we don't know. We have to find out where the LCD is actually physically connected into this interface here. But yeah, there you go. I mean, this is going to be handling all of your main front panel, your user interface functions, your operating system, your main display stuff, of course, all your menus and everything else. It's going to be handling all that. Whether or not it's actually the real live data, real live waveform data directly to the screen, I mean, they could be mapping it through this ASIC up here. You know, that'd be a better guess than trying to funnel everything into this poor little applications processor, even though it is pretty beefy. Yeah, it's more likely to be handled up here, the display parts of it. That's what they do in the Agilent ones, for example, or the ASIC handles the direct mapping of the waveform to the screen, and then the main processor just sends the data to that processor, which then, you know, adds the menus and cursors and everything else around, wrapping around or overlaying that waveform data. So you can get the fast waveform updating, and of course all your menus and everything else, they can be slow as a wet week, and you don't care. And there's nothing else terribly exciting on here. We've got a couple of push buttons down here. CPU power on, off. Very interesting. Global reset. Built-in switches like this. PCB mount. They've gone to a bit of trouble to mount those things in for design, development and servicing and stuff like that. I don't know. Yeah, we've got another big multi-channel switch mode supply up here doing some stuff. I'm not sure why they did that on the board, and they've got this full main power supply board all out here doing stuff. But anyway, big multi-channel, big multi-way connector up here connecting the main power supply board on. They've got some miscellaneous stuff down here that's just handling the USB port, the front panel USB port down the bottom, so nothing terribly exciting there. So that's the main overview of this board. Not a huge amount on there, but as you'd expect, or, you know, Tektronix go to town in terms of developing custom ASICs and, you know, really engineering this thing to the hilt to get the cost down. And, well, we've got three main heatsink devices over here. Obviously, two of them are identical and handling 2 channels each. We've got a third one which handles all 4 in some way. We've got this mysterious FPGA over here doing something with some ROMs hooked up to it. We've got a main Tektronix ASIC over here, not heatsunk, curiously. We've got an applications processor which handles all the real-time OS, and we've got our logic analyzer stuff down here, and, well, there's not a huge amount more. Okay, let's lift this main processor board out. Ta-da! Haha, we're in. And here's the main board, and it's pretty much what you'd expect. Not much on the bottom apart from some additional memories just to get the density. It makes sense to put them on the back just from a PCB routing point of view. Flip them on the other side of the other chip on the top. It just, you know, it works out fairly well. So here are your 3 main heatsink ASICs. One of these per sharing channel. We've got some extra memory over here. So we've now got a total of 2 gigabits memory per channel. There you go. And of course our main ASIC in here coupling all 2 channels together. There's nothing else on the back of that FPGA over there. Of course, there's our logic analyzer input connector. That's actually the front panel connector there. We've got some more high-speed comparators on the front end there, but apart from that, not much else. Here's our main Tektronix ASIC down here. Yes, we've got more memory coupled around that, so tons of it. Got 2 high-speed board-to-board interconnects, and they're going to be actually bringing the data over from the front ends. Presumably, this is where the systems engineering in this gets interesting because you notice the ADCs, well, the front ends, sorry, are not on this board. They're on the other board, and they've got to get across. The data's got to get across, well, this high-speed connector here, because this one over here is coupling in some other stuff over here to the main Tektronix processor ASIC over here. So, yeah, go figure. We do have an extra memory up here on our ARM applications processor over there, but apart from that, not much else. By the way, I just checked the photos from the MDO 4000 teardown, and the main Tektronix ASIC here on the 4000 was the Tech 0005B. So this is presumably a new revision of that part. Now here's where the surprising part comes in. Just like the MDO 4000, yes, they have a separate input board here which contains the analog front ends. These are the 1 GHz front ends, 4-channel scope of course, and this is our RF front end over here, but that's all there is to it. I'll show you a photo from the Tektronix MDO 4000, and it was much bigger like this, and that contained all the big RF CAN all up there for all of the spectrum analyzer stuff. But look, there's nothing else inside this thing. All we've got is this tiny RF front end over here. No wonder they're keeping the cost down on this thing. This thing is nothing like the MDO 4000, and not only in the spectrum analyzer part of things, but also there's no ADCs on this board directly, at least not on this side. Once again, here's a photo from the MDO 4000, and it had above each one of these each one of these analog front ends here, it had a separate ADC per channel with a big heatsink on it protruding up through the top side of the main processor board. The heatsink was so big it had to go up through cutouts in the main board. This has none of that. Where are the ADCs? These are the analog front ends, 1 GHz bandwidth, but hey, are they just taking the analog data through this connector here? Anyway, if you send your scope back to Tektronix to upgrade it from the 100 to 500 MHz version to the 1 GHz version I've got here, this is the board they will swap, no doubt. The processor board would still all remain exactly the same, but they just swapped this board over. Not a huge amount of cost in this thing. I was expecting basically a similar analog or RF section to the MDO 4000, but it's nothing like it. Just this tiny can over here. I doubt there's anything on the flip side of this. It's just going to be the front panel, the keyboard, and stuff like that. We will go further to try and find out, but they've really completely re-engineered this by the looks of it and built it down to a cost. And because the MDO 4000 was, a ridiculously expensive scope, incredibly, versatile, but very, very expensive. They've done some serious re-engineering to get the cost down for this MDO 3000. That's why they can afford to include the RF spectrum analyzer onto, the base model 100 MHz dual channel scope. That's it. And they software limit the RF bandwidth. So this is going to be a 3 GHz RF spectrum analyzer, regardless of whether or not you buy the cheapest 100 MHz model. But granted, as I said right at the start, the 100 MHz model dual channel is $3,300 or thereabouts, starts from that price, and that only includes a software limited 100 MHz front end. But the full 3 GHz front end is there, but obviously it's not your traditional spectrum analyzer. There's nothing in there. Now I'll take this board out as well, of course, but there is not going to be any analog to digital converter on this board, because when you start talking, 5 gig samples per second ADC, right, you need some serious heat sinking. That's what that board over there is, right? These are still going to be your ADCs sharing 2 channels there. But the difference, the MDO 4000 had them directly coupled on this board. So the only thing that can be happening here is they've got the differential analog signal from the buffer here coming out. It's probably this trace here. Look, you can see it's snaking its way up there. They've got some length matching on that, going through something there and going into this connector. So they've got the analog signal running through this high-speed connector over here. Nothing inherently wrong with that. You're just driving it a little bit more distance. These connectors are really, expensive and really well engineered for that sort of thing. And of course, they'd have alternate grounds and pins and all sorts of stuff going on in there to ensure that there's no crosstalk and stuff like that. So, it's not bad, but yeah, they're running the analog connectors over that board-to-board, analog signals for all 4 channels over that thing. Yeah, look, they're obviously matching the length. You can see this one over here. This pair goes all the way over there, and they go, oh, this one is physically closer, so we have to match the length of that pair, because you can't just have different length pairs. Oh, the propagation layer's screwed, so that's why they have to switch it back there, so the length of that trace would be precisely matched to the length of that one, and this one here as well. You can see it. Here it is, running in here for this channel 3, I guess it is, and snaking up there, all around there, down there, and back up and into there. Woo! And the other fascinating thing is, look, we've found our display connector. There it is. There's a ribbon cable going off to the display. And all it is going through a buffer over here, coming from this main board-to-board interconnect, which goes up to the main processor board. Wow, they're going via this power supply board here. Whew, why? So coming back to our main processor board here is our board-to-board interconnect. This is the only thing that the front panel display and keyboard has to go through. And unfortunately, I can't see the traces on either side of those. So they're obviously running in the middle layers of this board somewhere. Now, where they're actually running to, my guess would be that they're running over to this Tech ASIC over here, and then that, as I said, is the main applications processor is mapping any required user interface data over this main Tech ASIC, which is then driving the display, exactly how it works in the Agilent X series scopes. But that's only a guess. I do stand to be corrected on that. It could very well be coupled directly into the applications processor. But as I said, that's not going to handle a couple of 100,000 waveform. All your waveform update processing is going to be done in this main Tech ASIC. All your DPO stuff and things like that is definitely going to be done in here. And whether or not they're actually transferring that and just updating at a slower rate to the screen, they could certainly well be. They could certainly be actually doing that, because there is a big difference between the waveform update rate, i.e. the processing waveform update rate of this thing. I think is like 250,000 waveforms updates per second. There's a big difference between that. That doesn't necessarily mean that that information is being updated on the screen, of course, at 250,000 waveform updates per second. It's not. It's being done in memory, and then a slower version of that, a slower copy of that information, is being transferred to the display. So it could certainly, all the DPO is certainly happening in here, but it could be funneled, and all the processing for the display is done via the applications processor. Actually, that might make more sense, because this does have a big display processing engine in it and driver as well. And it does look like inside this thing they've got one huge PCB on the front here. You can see this matte black PCB material here with the pins for the intelligent probes which actually plug onto this thing. I think there's one big matte black board covering this whole front panel. And you can see that it extends up here to these plug-in application modules as well, with the contacts directly on the board. And by the way, for those wondering, the spectrum analyzer over here, this is literally going to be just the front end amplifier and attenuators and everything else for the spectrum analyzer. After that, it's purely digital. And I believe I read somewhere that it's doing, because this has a very wide capture bandwidth, by the way, 1 gigahertz wide capture bandwidth, absolutely fantastic if you need to resolve and capture and debug different signals over an entire, you might have something operating at 400 megahertz and you have something else operating at 800. This is a way to really capture the whole bandwidth at once and see time correlation between the two signals. Now, speaking of which, the time correlation for this MDO 3000 is not the same as the MDO 4000. They've deliberately cut the performance in this thing down completely so that you cannot do simultaneous time sampling and correlation between the spectrum analyzer and between the analog inputs as well. And that's an incredible shame, and one of the big disadvantages of this thing is that, you know, one of the huge advantages of the MDO 4000 was that you could do that fantastic magical time correlation between your analog signals and your RF signals and your digital signals as well, hence the mixed domain name. So this thing almost doesn't deserve the mixed domain name, because if you can't do time correlation and sample at the same time between the RF channel and the analog inputs, well, what's the point? It's just a tacked on spectrum analyzer in a box. Anyway, enough ranting about that. Yeah, this is just an RF front end, that's it. I read somewhere that it's doing, it's sampling this, the 3 gigahertz bandwidth is being sampled at 10 gig samples per second. So I reckon they're tying, well, obviously the analog channels are being sampled at 5 gig samples per second. They're obviously tying at least 2 of those, maybe even 4 of those together to sample the RF front end. And hence why you can't do time correlation between the and sample at the same time between the RF channel and the analog channels, because, well, when it's sampling the RF, it's working as a spectrum analyzer sampling that RF front end, it needs all the power of those ADCs, which are over here on this board, to actually do that. And then it's got no resources left over for the analog channels at the same time. So you either use this as a spectrum analyzer or as a regular time domain oscilloscope. What I've done is I've undone 4 machine screws down in here, or 3 actually, and it looks like we might be able to lift this out independently of the rest of the chassis. So let me carefully lift this sucker out. Yeah, she's coming out. Oh, look at that. That is a beautiful design. Aha! Tons more stuff on the back. So I'm actually quite impressed by the design of this thing, the modularity and the way that you can service it and or assemble the thing. Fantastic. I was afraid that I'd have to take out this entire chassis. I actually started to take out the main self-tapper screws here, which go into the front panel plastic. I thought all that'd have to lift out, but it doesn't. I just lifted out this RF board here, the RF and analog front end board. Fantastic. Obviously, because it is designed, they put some thought into this design for that upgradability, because when you, as I said, if you send your scope back and you decide you want to pay the extra and get the 1 gigahertz version, well, they have to make the upgrade of this board really easy, and they've done so. Fantastic. And you can see, I think I was right about the front panel connector. Maybe you can't see it due to the exposure of the camera, but there is one big matte black board going right on the front panel. I may not actually get that far in the teardown because there's nothing interesting on there. And that's it. Check it out. Look, they haven't even bothered to shield the front side, put a can on the front side of this RF front end. It is so incredibly simple compared to the MDO 4000, which was more traditional, spectrum analyzer sort of construction and design as well. We'll take a look, try and see what that little puppy in there is. Obviously, look at all the via stitching around here. They're obviously getting a super low, well, in fact, all the way around here, obviously getting super low inductance ground path there, but yeah, they're not bothering to shield the top like they did. There you go, they got the can on the front side there, so we'll try and open that up and get a look at the RF front end, but that is all there is to it. Unbelievable. Looks like some sort of little processor over here just controlling the front end. Now I am sorry, but I will not be able to show you the 1 gigahertz analog front end because these solder connections here, here and over there are the metal shielding cans over the 1 gig front end. So this is the back side of it here, so they've obviously got a chip. There we go, it's like some sort of heat sunk QFN package, something like that, so they've got a bit of heat sinking on the bottom side of there. So all of your good stuff for the RF front end is on the other side of the board. Sorry about that. Some HCT04 logic here, old school 7400, can't beat it. You got to have that somewhere. There's one of those per channel. And further on up each channel, 3 6-pin SOT23s, not sure what they're doing. Probably regulation by the huge traces going in and out like that with the huge vias and the decoupling. So they're probably local voltage regulation for the front end. and we have ourselves a Maxim Max 9601. And that is no surprises a high-speed Peckel comparator for the triggering, obviously the triggering front end. So there you go, that's the proper analog triggering section, 500 picoseconds, you know, really kick-ass comparator there. And I don't know what that one there is doing, 441LAA, I don't know, you could try and figure that out. Don't even know that symbol offhand, but anyway, one of those per channel, so we're basically looking at a duplication of all that circuitry all there across all 4 channels. And backside of that RS spectrum analyzer, no real surprises. It's another ADF 4360, exactly the same part we saw on the main logic board. That is the synthesizer and VCO to generate the sampling clock required. And curiosity is going to get the better of me, so I'm going to lift up that label, lift up the skirt, see what that thing is. Of course, it's a dead giveaway it's some sort of processor, because anyone that has a label like this means it's been flashed and has code in it. Yeah, there you go, little Freescale HS8 8-bit processor. Freescale, of course, well, they use a Freescale main applications processor, so hey, might as well use the same manufacturer for your little 8-bit micro. Now these traces are interesting. Look at these, all these high-speed differential pairs all going over to this connector on this far side of the board. I thought they'd all be popping out that middle one, but they're not. There's a ton going over to here. Now here's where we look at the systems engineering and see where all this stuff is flowing to figure out what's going on. We know we've got these high-speed differential pairs, one coming from each channel, probably even from the RF channel over here. So there's a whole bunch of them going to this connector over here. And where's that one connected? Well, if we have a look at our main board here, it's this connector over here. What is that connector near? That main Tektronix ASIC over here. Here's the other one. So as I said, all of the analog channels would be going through this connector through to ADC1 and ADC2 here, which handle all 4 channels, but then they've got a whole bunch of other pairs coming over here, coming out of, if you have a look, where they're coming out of, that chip we had a look at down in there, which is your high-speed comparator for your trigger. So these are actually the triggering outputs from each channel going through that connector, and that connector pops up here. There it is, it's mounted on the back side of that there, coupled into this main Tektronix ASIC over here. So this is handling all of the triggering. But of course, if that's handling all of your triggering, then what is this third device over here? These are obviously your main ADCs and acquisition ASICs. As I said, 1 per 2 channels there. Well, what's that third common device doing between all 4 channels if it's not doing the triggering? Check out this. Someone was thinking when they laid out this board, look at this. They've put notes to whoever was designing the case or the system, putting the whole thing together. The person who laid out the board went, oh, okay, it's important we don't short out the positive tab of this battery to anything because it's a through hole part. If we accidentally short that pin out to some metal, or if it's very, very close, that could, in production or something like that with tolerances, short out to one of the metal cases or something like that, then, well, it's going to ruin your day. So they've put a radius around there where we must cover, or whoever designs the next part of the system must cover that pin there. And look, even may cover. Hey, if you want to gild the lily, let's may cover that part. And they've followed that up with it on the bottom, just in case you missed it. Look at that. Brilliant. And of course, we can't let this go without having a peek in the RF section. I've undone 3 screws there. Yes, we have our gasket. Look at that, completely separated. You can see the signal path, how there's the RF connector there. It's flowing up through here, flowing up around there, and out, well, there, somewhere. It's popping out on the top side. So let's take that aside and flip our board over and see what we have. Hey! Not much. There we go. No solder mask on there. That's pretty typical, but there's hardly anything in that front end at all. And as you can see, it follows the path directly that was covered with our metal die-cast top on there, and that's very typical of these spectrum analyzers construction, or controlled impedance, of course, or very critically designed. We've got some length matching around there, and basically when you're talking in the gigahertz range, everything on your PCB becomes a component. I've talked at this before extensively on previous videos, and how you can actually have distributed element filters manufactured out of your PCB, bandwidth, low pass, high pass bandwidth filters manufactured magically into the traces of your PCB. Doesn't seem to be a huge amount of that going on here, or any of that going on here really. All I see is there's our input, there's our AC coupling, and then we've got some filter in there on the input. We'll have a look at what that is. That's our input amp, and then yeah, we've got some more in series termination here, some more AC coupling going on. We'll have a look at that, but some more filtering happening around there. Little transformer coupled, little balun, sorry, going there, and well, not a huge amount else. Now, if you're concerned about those solder joints, I know they look ugly, but that's what happens with when a high thermal mass component meets lead-free solder. It looks pretty horrid like that, but no, there's nothing actually inherently wrong with that. And smack on the input here, no surprises for finding that we've got an attenuator chip. In this case, it's a Hittite brand, Hittite Microwave Corporation, HMC 624 LP4. It's a digital attenuator, i.e. by digital, it means that it's got a digital serial interface, serial or parallel interface controlling the attenuation in there. So yeah, we basically just got our AC coupled input, a little bit of filtering happening there, and it goes straight to the attenuator, which gives your input or your input attenuation ranges. And as always, I will link in all the data sheets down below so you can go and check these out for yourself and follow through. And what do you need after an attenuator? Well, you need your amplifier, of course, and yeah, once again, we've got a Hittite Corporation. Hey, if you're going to get all your stuff, you may as well get it from the one company, especially the company who specializes in these sort of chipsets for these sort of RF front ends. And this is a DC to 6 gigahertz gain block. It's the HMC 311, and oh, for all you RF fans, it is a heterojunction bipolar transistor amplifier, a HBT with 14.5 dB of gain. Fantastic. And you might notice, if you look very, very carefully, it might be a bit puzzling that there's no other pins connected except the input and the output pin. How does that work? How does a chip like this work if there is no power pin at all? In fact, this is true. Take a look at the data sheet here. There is only an input and an output pin. There's no power pin. How does it work? Well, easy. Read further down in the data sheet and you'll see that the power is actually coupled in via the output here, via this inductor here. There we go. So it's coupled into the output, powers the chip internally. This is very common for these sorts of RF amplifiers. And you'll find these in all sorts of things, like you might be familiar with your TV masthead amplifier, for example. It'll be a similar thing. You feed in your voltage down at your, at your TV outlet. You actually feed it up the coax, and it's powered from the output. Exactly the same thing happening here. Oops, and I forgot, before and after that, little 8-pin packages here labeled 360. I don't know what they are. There's no equivalent, HMC 360 from Hittite or something like that. But basically, based on the operation of this thing, there we go. There's our input attenuator, our digital attenuator from our RF front end. So our RF comes in, goes through our digital attenuator, and obviously you can see that there's a bypass trace here, of course, controlled impedance trace going over and bypassing our amplifier, our gain block there. So obviously these are little RF switches that digital line there would switch between, switch to bypass completely our RF amplifier there. And then we've got our signal coming out of our filter here, going up to what looks like a little transformer, and that will be a balun, of course, because at this stage we're still operating single-ended. It is not a differential pair. It is a single-ended reference to the ground. You can see all the via stitching around here. Oh, beautiful low impedance. And you'll see that out of the other side of the balun here, bingo, it comes out differential. So we're no longer referenced to ground at this point. But curiously, then it just pops out, does some extra, it looks like we've got some load matching there, and looks like, no, there was supposed to be like some filtering happening there, but I don't know. And then we've got some extra delay introduced by this trace around here, and then they're basically just joining up again, single-ended over at this side, so not sure why they've actually done that. And this is where it ends. And, well, curiously, you've got to think, well, a spectrum analyzer, it's got to have that VCO, got to have that local oscillator. And here it is. It's a, once again, Hittite HMC 429, and it's a 4.45 to 5 gigahertz VCO. And that's all it does. It just basically, voltage input, it can generate a frequency out within that range. So at this point I started to get rather confused actually, because, well, we've got ourselves that VCO there, and anyone who knows the basic operation of a traditional spectrum analyzer, which you've seen in many of my previous videos, once you see, well, they have a VCO like that, and the VCO feeds into a mixer along with the RF signal, goes into the other side of the mixer, and bingo, out the other side pops your intermediate frequency IF signal, which then goes on to further pass down in the spectrum analyzer. And, well, we've got a VCO here, so I thought, well, okay, there's going to be your traditional mixer in this thing, but, well, it just didn't make sense. I mean, where is the mixer in those two little white 4-pin white things there, and a couple of traces with some termination? It just didn't make sense. So I contacted fellow blogger Alan Wolke. If you haven't subscribed to his YouTube channel, you certainly should, who actually is an applications engineer at Tektronix, and he wasn't quite sure either exactly how this new product actually worked, but he had a couple of ideas, and, well, it started to make some more sense. Now, there's one thing which we both knew, was that the Tektronix MDO technology actually samples the RF, the entire RF spectrum, in this case at 10 gigahertz. So obviously it combines the traditional ADCs in the oscilloscope and uses those to do the sampling directly on the RF spectrum. But hey, we had this VCO in here, right, acting as a local oscillator. And when you've got a local oscillator in a spectrum analyzer, it implies that it feeds into a mixer and your RF comes in and you get that intermediate frequency out. So, you know, we didn't quite know what was going on, but Alan knew that there was a technique where you dither where you inject a dithered RF signal into the RF signal you're trying to measure, and then sample that, and that would increase your performance of your RF front end. And bingo, he pulled up a rather obscure, I think, application note or white paper from Tektronix that explains exactly how the MDO RF spectrum technology works. And this was the other thing that was puzzling me. I didn't quite understand how they were getting the performance out of this spectrum analyzer when they were using just the regular ADC in the oscilloscope. Sure, they're sampling at a high sample rate. In this case, they're combining all the ADCs together, presumably to give that 10 gig sample per second sample rate for our 3 gigahertz RF bandwidth. So they're sampling the RF directly doing that. But hey, what's the difference between just a regular oscilloscope with an FFT function and this Tektronix MDO technology? You know, yeah, you can do some boxcar averaging like you're familiar with the high-res mode and stuff like that, but we didn't have the extra bandwidth there. You can do some other averaging and things like that, but it just didn't make sense. I mean, an 8-bit converter at best is only going to get, you know, around about that 50 dB dynamic range. And, well, this spectrum analyzer has, you know, it's got like 100 dB, in the order of 100 dB dynamic range. So how do they get that increased performance using an 8-bit converter? And here's the white paper I was referring to. Now, I will link this in down below, so if you want to read all the gory details yourself, you certainly can. And, well, here it is. Learn how the MDO series scopes, including the 3000, this is for the 4000, but it will apply to the 3000 with, the subtraction of something we'll show in a minute. They're able to leverage existing oscilloscope acquisition technology to achieve spectral fidelity on par with entry-level spectrum analyzers. So the design techniques used in the MDO series allow them to achieve that fidelity far in excess of that provided by the typical FFT feature found in other oscilloscopes, and that is the key point of difference, even though they're using exactly the same 8-bit ADC. Now, let's take a look at the basic block diagram here, and it's this is for the 4000. So the 3000, in fact, they're actually missing something out of here, which we'll show in a minute as well, even on the 4000, which what we're doing. Basically, the RF input can is just here, which is what we've seen. Well, at this point, that's all it is. Input attenuator, some gain, some some low pass filtering and stuff like that, but it's basically just an RF front end amplifier, and it's going into what's called a block down converter because in the MDO 4000 series, well, they're trying to get up to 6 gigahertz bandwidth, but we don't need that in the MDO 3000 bandwidth because we're only going to 3 gigahertz here. So we're just operating within that one block. So we don't need a block frequency down converter. So that is gone out of the MDO 3000. And then, well, yeah, a trigger signal comes out of that and it just goes into an analog digital converter. In this case, it'll be all of the ADCs that are regularly used on the analog channels. They tie them all together so they can get 10 gig samples per second. So massively high sample rate. And as it says further on, here we go, a bandwidth in excess of 5 gigahertz. So the actual ADC itself has an input bandwidth up to 5 gig. The ADC hybrid or whatever ASIC developed by Tektronix, that massive 5 gig bandwidth, so they can easily get a 3 gig input spectrum analyzer. They can sample the RF signal directly. So, you know, none of your traditional spectrum analyzer type stuff. It's basically just operating like a regular scope. That's pretty much all it is, except, you've got some nicer RF sort of front end with your 50 ohm load and your attenuator and your gain and, some filtering and that sort of stuff. But apart from that, it's just like another analog channel, really. And as such, you can forget about all the rest because, well, yeah, it does some digital down conversion and stuff like that and some discrete Fourier transform, which they don't show in here, but that's all just your digital processing inside the thing. It's basically RF straight into your analog to digital converter, except for something that, but how does it do that exactly? How does it get like 100 dB of dynamic range instead of 50 dB you'd expect with your regular 8-bit analog to digital converter? Well, it's not using averaging. It's basically using three different things effectively, but processing gain is one of the main ones, which is all done in the digital domain. I won't bore you with the formulas and stuff like that, but it's basically saying what I've been saying is that a regular 8-bit converter only gives you 50 dB noise floor. That's pretty much it. But we're after in a spectrum analyzer like 100 dB for a half decent entry level spectrum analyzer. So that's what we're getting still with that 8-bit ADC. But what they can do is they can do some digital down conversion and some discrete Fourier transforms in the software after the ADC. So this is all software processing, and that gives you what's called process gain, which effectively lowers your noise floor because it's over a smaller bandwidth and it can calculate and do all that in digital. So even with an 8-bit ADC, you can get a noise floor down at minus 100 dB. Fantastic. Oh, magic. And there you go, they give you an example of a 10 megahertz span, for example, and a resolution bandwidth of 10 megahertz with the 10 gig sample per second, MDO 4000 and MDO 3000 samples at the same rate. In this respect, they are the same instrument working the same way. So that improves the signal to noise ratio by roughly 57 dB, massive. So they get 107 dB noise floor out of an 8-bit converter. Unbelievable. And they go on to say that a traditional spectrum analyzer, like modern ones, they're also doing digital ADC sampling. You know, very few of them are, you know, really true analog anymore, but they're very low sample rates. So if they're sampling at like 20 meg samples per second, it requires a 12.5 bit ADC to get the same signal to noise ratio as they can use an 8-bit ADC in the MDO series scopes. And of course, hey, you're already paying for that 8-bit ADC inside your oscilloscope, so why not use it? It's very clever. But there's one more trick up their sleeve which confused us in the teardown, because there was that local oscillator in there, that VCO chip. What the hell was that doing in there? Well, it was adding dither into the RF signal before the ADC to increase the spurious free dynamic range. And they explain exactly how that works here. I won't bore you with all the details, but basically, it does this in the MDO 4000 as well, but they don't show it on the block diagram. But in the MDO 3000, it's much simpler because there's no block down conversion. There's no IF frequency or mix or anything like that. The RF just goes straight into the ADC, but they add in, or they mix in, a dither signal like that. And basically a dither signal is just a random noise, and of course the VCO, the output frequency, changes based on the input voltage here. So you put a random signal on there, you're going to adjust your frequency, or dither your frequency that is added onto there, and that reduces your spurious free dynamic range by spreading it over your entire range of your a wider range of your ADC. But yeah, you can read the white paper if you want to know how it works. So there's no block down converter in the MDO 3000. It's just the RF straight in, and then they add the dither signal on here straight in the ADC. Now the dither signal has to be just below, somewhere just below the Nyquist sampling Nyquist frequency. Of course, we've got 10 gig samples per second here, so it has to be somewhere under 5 gig. And of course, as we saw in the datasheet, this HMC 429 VCO is designed for just under 5 gig. Perfect chip to add some dithering into there. So that's all they got. So that's the only cost that they're adding to this thing, is this VCO. It's just some RF attenuating and some switching and some amplification. That's it. Bang, straight into the existing analog to digital converter in that you're using for the analog channels, and Bob's your uncle. So the result of all this, RF and digital processing magic is that they're able to leverage the existing analog to digital converter already in the scope, and to add some low-cost RF input parts that, as I said, only cost like, $25-30 tops, and bingo, you got yourself a full 3 gig bandwidth spectrum analyzer that has a massive capture bandwidth over effectively the whole range, or 1 gig capture bandwidth, I think, in the case of the MDO 3000. It's absolutely incredible that you can get this performance. Of course, it is not as good a performance as a proper, well-designed spectrum analyzer with a better ADC in here, of course, but hey, it matches the performance. It's going to be similar to entry-level spectrum analyzers on the market, and hey, that's good enough when you include in just some basic spectrum analyzer functionality into a scope. It's brilliant. Unless they've got this thing patented, I expect all the other manufacturers are going to start doing this with, in the not too distant future. But I suspect, as with a lot of things, it's probably not as simplistic as it looks. You can't just whack it in there and do a couple of routines and Bob's your uncle, you got yourself a spectrum analyzer. There's probably a bit of secret sauce and some, tongue angle, greybeard tweaking that goes on inside this thing to actually get it to work really well. But still, hey, you can get that spectrum analyzer for a low cost. It's brilliant. Alright, I haven't put it fully back together yet, but I'm curious to know what happens when you power it up, without that communications, with the case open like this, and without the comms board plugged into it, and also I want to see what that mysterious, I think, finger touch switch does. So, I don't know, let's give it a go. Only one way to find out. And here we go. Whoop. We have some lights. No. Yes. Booting up. I didn't have to touch the power switch, which is a soft power switch, by the way. Ta-da! Come on. Twiddle thumbs. See how long it takes to boot up. Quite a lot. I think it takes like 30 seconds or something. I think it's on par with the Agilent. Haven't actually timed it yet. Ta-da! And it's getting there. It's getting there. It's getting there. It's getting there. Not yet. Oh dear. There we go. We're on. Power on self-test failed. If the error persists after power cycling, refer to the oscilloscope to qualified repair personnel. There you go. You can proceed. If it's possible, proceed. Menu off. However, the oscilloscope may not perform. There we go. Menu off. Warning, the oscilloscope is not compensated. Ta-da! But it has booted up. And if we push our RF button over here, there we go. Our RF is sampling. So, let's, I found a bug in this, by the way. Check it out. If you press the RF button again to turn it off, you would think it would go back to your digital channels, but watch this. It doesn't. It just freezes. Dumb. Oh, well, it hasn't actually locked up, but anyway, just press that and you're back. So, RF takes you into that, and then going back, you know, you can just press that and you're back in, but just a silly little thing. Now, I'm curious to know what happens when you touch that magic finger sensor. Only one way to find out. Nothing. Bummer. Whoa, look at that. Warning, internal temperature is approaching a point where the oscilloscope could be damaged if you continue. Check that the fans are operating and there's sufficient clearance, blah, blah, blah. Whew. Yeah, tech scopes, they run hot. Alright, well, let's do a quick uncalibrated temperature of this thing with my FLIR E8. Look at that. I mean, I don't want to leave this thing here for too long, but yeah, I mean, well, they're silver heat sinks, so I may not have the emissivity set correct and all that sort of stuff, but we're talking, you know, 50 degrees at least. Those heat sinks, there's a real hot spot up in there, 50 on the other side of the board there, so I'm not sure what's going on there. But anyway, this thing, I think it did actually automatically switch off. So, yeah, it's definitely got some sort of internal temperature measurement, and it does not like being operated with the case off, that's for sure. I mean, it was barely up for like a minute before, 2 minutes before that warning came on. And yep, there we go, I just pressed stop and it switched itself off. So, yeah, well, at least it won't damage itself, hopefully. And of course, system airflow wise, that's why they've got the fan in this position, and that's why they've got it blowing inwards. The air is sucked in from the outside here, from this vent on the outside, sucked in directly over, wham, right on top of the 3 main heat sinks here, across the board, and then out the other side up there. And no, the fan is not very loud in this thing for those who are concerned about that thing. It looks like it does have variable speed on the fan because you can hear it sort of whir up as soon as you turn it on. It goes and then it's quite a low level hum. It really is, you know, not that distracting. And there you go, it even logs that fire. Warning, during the previous power on session, the oscilloscope automatically shut itself off due to excessive internal temperature. Check that the fans are operating, that there is sufficient clearance for airflow. Now, I'm not sure whether or not I'm supposed to be impressed by that or not. Impressed by the fact that, well, the design engineers have thought of that. Like, you know, to actually put that menu in there, they're sensing the temperature, it'll automatically shut down. That's all really great, but you can't help but wonder, well, why is it shutting down in the first place? Is it that critical that, you know, like less than 2 minutes after, probably, you know, only a matter of a minute or two after you power it on, it shuts down due to over temp? I mean, geez, what, it can't last 10 minutes before the die gets up to temperature that it's obviously sensing? I don't know. I get the sense that maybe there's, you know, marginal thermal performance on this thing. Perhaps. I don't know. But hey, this is Tektronix. I'm sure they know what they're doing, but they do have a bit of a history of with their stuff running hot, that's for sure. But with heat, of course, comes performance, usually. Unless they're really piss poor. But anyway, here it is. We'll only find out if its performance is great when we do the review, which will be coming up, of course. And in case you're wondering, does it work? Well, yes it does. Here's my RF signal generator, 100 megahertz, minus 10 dBm, and there's the signal. There we go. Almost bang on 100 megahertz, minus 10.3 dBm. Not a problem. And I just finished putting this thing back together, and damn it, I forgot that it has 6 instruments in one, and one of them is the arbitrary function generator, and that's on the output here, and clearly that's on this board which connects into the PCI slot, this board which handles a ton of stuff on the output. No wonder they have to put this little heatsink on this little beastie. Obviously, there's some sort of, probably some sort of FPGA. I don't know if it would be a custom device or anything like that, but clearly they're doing something to generate the AFG on this, because I didn't see any arbitrary waveform stuff on the other board, and it makes sense, of course, to put it on here. We've got some output relay switch in here, and well, to switch in the 50 ohm load termination and stuff like that. So this looks like function generator circuitry, and obviously some sort of FPGA or some other controller to handle it. We always forget about the line frequency trigger. There it is. They've just got 2 wires heat shrunk over the mains cable there. No, that is not making any direct connection. It's just a, a proximity, a capacitive coupling thing, and that's coupled into that little chip down there. Not sure what it is. Couldn't be bothered reading the number. Anyway, that does your line trigger in 50 or 60 hertz, depending on where you are. 50 hertz here in Australia. Once again, a high-speed comparator, ADCMP 562. So it looks like we don't have at least I can't see any DDS generator, so it's obviously doing it internally. Well, it is a full ARB generator, of course, so yeah, most likely it's just doing it completely internally inside that FPGA or whatever that beast is. So yes, the entire ARB generator seems to be that single chip there, and pretty much just miscellaneous support stuff. There really doesn't seem to be anything else happening there. There's our output buffer there, obviously, with our 50 ohm output terminator switchable with the relay, and that just goes to the output, and that's it. I mean, yeah, they haven't added much cost there at all. So there you have it. I hope you enjoyed the teardown of this new, brand spanking new Tektronix MDO 3000 scope, and yes, it is a bit of a game changer. The MDO 4000, its big brother, was a game changer in that you could get that mixed domain debugging capability, which was so fantastic, but whoa, did you pay a price premium for it. But now with this sucker, they've brought it down into the affordable mid-level domain to compete with, well, their major competitor, obviously the Agilent 3000 X series, and they're about equivalent on price. The base model, absolute bare bones, 100 megahertz dual channel version of this is about $3,300 US, and the Agilent one is about $3,200 or something. It's a little bit cheaper for the equivalent bandwidth and number of channels, but this sucker, you get the RF spectrum analyzer built in, 3 gigahertz capable, of course, but hey, everything's optional extra with these companies, so that's an extra $2,500 if you want to enable the 3 gig spectrum analyzer front end. But at least you do get it built in the base model up to the bandwidth with your scope. So you buy the 100 megahertz model, you get at least 100 megahertz spectrum analyzer, which is better than just the FFT built into a regular scope. It's got better performance than that. So really, that is quite interesting, and it will be very interesting to see what the competitors do if they eventually bring out a mixed domain scope as well. Well, they might be already working on them since Tektronix released the big brother MDO 4000, but I found this rather interesting teardown. I expected a lot more in here, but they haven't. They've really gotten the price down, the system integration. They seem to have done a lot of work in that respect to actually get the price of this sucker down. And yeah, there's a performance hit in that respect, in that it's not a true mixed domain oscilloscope anymore like the MDO 4000 series, and that was the huge advantage of that. You could actually capture the RF and your analog and your digital all at the same time, so it was truly a mixed domain. This really isn't. You have to choose either the spectrum analyzer or the analog front end, so a bit disappointing in that, but hey, you effectively get the spectrum analyzer thrown in for free. So really, you can't complain. Now, I did look at the bill of materials cost. I thought they were being a bit silly with this thing by bundling in the spectrum analyzer built in, but as we've seen, there's hardly any circuitry in there at all, and I actually costed it out, all the main chips, and even at DigiKey prices, we're only talking $25 to $30 in 10,000 quantity at DigiKey prices for the Spectrum Analyzer functionality. That doesn't include the connector or the RF die-cast can or something like that, but you know, even then, it should be well under $50 BOM cost added just for a full 3 GHz Spectrum Analyzer. So that's a bit of a killer. Unfortunately, you do have to pay for it with the software options, but anyway, this is a really nice competitive scope. I haven't used it all that much yet, and a review will follow, of course. But I hope you found the teardown interesting, because they have done a few interesting things in here to make it competitive. Awesome. Tech are back. Excellent. So if you want to see those high-res photos, as I said, check out the eevblog.com. Link is down below. And as always, there's a forum link down below where you can discuss this thing to your heart's content. There you go. And as always, if you like the video, give it a big thumbs up. Beauty. Catch you next time.